Good morning everyone, I am Mr. Ish. Thank you for joining me. In this video I want us to solidify our technique with regards to solving this particular style of second order differential equation, which is of the linear homogeneous style. I've presented a video where we've looked at several styles. You can refer back to that video, but this right here is a linear homogeneous. You have everything here equaling to a zero, but you have a linear style of differential equation. But we are looking particularly here at the case where we will end up seeing two real roots. What does that mean? It basically means this: you're looking at the procedure where you are converting your second order linear homogeneous differential equation into an ordinary quadratic equation. You know the quadratic equation, ax squared plus bx plus c equals 0 style. In that, based on the discriminant, you can have two real solutions, you can have one real solution, or you can have two imaginary solutions. We are focusing on this form right here. We will look at three examples here, and I'll start here with this question. In all instances, look, the component d square y dx square is similar to your y double prime, your dy or dx is similar to y single prime. Those are your first and second order derivatives, but this right here represents your general equation form, what we're looking at. In our first question, this is y double prime plus y single prime minus 12y equals 0, a linear homogeneous equation. How can you solve this out? Your technique over here is to bring in a factor, and we can just be general here with our factor in terms of terminology. Your factor is basically e to the power of rx. Why is it an exponential? Because in terms of derivatives, these are easy. If you did the first order derivative here, you're looking at re to the rx. Here you know you have exponents involved. When you're looking at the second order derivative of this, you're looking at r squared e to the rx. These are the substitutions which come here into play. You have the y, the function is equal to this, your first order is equal to that, your second order is equal to that, and that's exactly where things will fall in. My second order here is r squared e to the rx plus your first order derivative re to the power of rx minus 12 e to the rx, because that's just your plain y, is equal to 0. You have to convert this into a quadratic equation by means of employing those substitutions. Isolate here e to the rx, and you're looking at r squared plus r minus 12 equals 0. And there it is, your quadratic equation. Your task now is to solve for r, but technically you can take this and you can zero it out, and you're left with only r squared plus r minus 12 is equal to 0, where your two real roots will develop. This thing can be equal to 0 because if you're solving for this component, you take this on the other side, 0 divided by this entire factor is zeros out. What are your values over here? Well, you're looking here at r plus 4 and r minus 3. And that tells you r is equal to minus 4 comma 3. Those are your two real solutions, but these have to come back into your original factor by means of the substitution. This is telling you clearly you're having a solution which will look something like this: e to the, let's put the positive exponent first, e to the 3x plus e to the minus 4x. Y is equal to that. But you could have had any combinations of these based on the coefficients and that coming into play, so you can do a and then a b. And this right here would represent your solution to this differential equation right over here. Your differential equation question is right here. And that right there is your answer. The reason why you put a and b, because this right here does not represent your unique solution, it represents your generalized solution. The generalized solution could have a variety of combinations of exponents. You could put a value of a, you could put a value of b, whatever they might be, then that would be your unique particular solution. Here, when you're solving these type of equations, you're presenting a generalized solution of your second order differential equation. This question has been completed. Remember, the main task is to convert your second order differential equation into an ordinary quadratic equation, and you solve for your two real roots. Let's look at this question. 3y double prime minus y single prime minus 2y equals 0. You know you're looking at 3 d square y or dx square minus dy or dx minus 2y equals 0. Everything else is still the same. The replacements or your substitutions, as you want to call it, they'll come right over here. You're looking at 3 and then r squared e to the rx. That's this substitution. Minus r e to the rx minus 2e to the rx is equal to 0. Isolate your e to the rx factor, and then you have 3r squared minus r minus 2 equals 0. Again, you could solve for this entire expression and push this, and you can zero it out. You're left with 3r squared minus r minus 2 equals 0. And that will give you your two real solutions, which will then play into your final answer. What can these factors be? You're looking at 3r and then you're looking at r. You just have to do your basic algebra over here, nothing more than that. You have a minus over here which is coming into play. So you're looking here at a minus 1 and then you're looking here at a plus 2. That's what you have. Therefore, r is equal to 1 comma minus 2 over 3. By convention, you want to put the positive one first in your final answer, and then you put a plus in between your two terms. Your solution here is y is equal to e to the rx, where r is equal to 1. You can just say 1x or just x, plus e to the minus 2 over 3x. You can put an a here and a b here, and that right there represents your answer. Remember, I'm used to using a's and b's, but someone else could use a different letter. You could have your answer presented in this way: c1, your one constant, e to the power of x, plus c2, your other constant, which here is synonymous with b, e to the power of minus 2 over 3x. Based on some type of questions, these x's could be t's. All of that has to be kept in mind, but we're looking here at y's and x's as our primary variables. I prefer to use a's and b's. This question has been done, not too hard. Let's look at one more. This represents our last question. Second order derivative of y plus first order derivative minus 7y equals 0. This will present a nuance or a particularity you need to be aware of. Not always can your quadratic equation be simplified easily, and sometimes you have to bring in the quadratic formula, which is what we will have to do here. Anyhow, bring those substitutions here. You're looking at r squared e to the rx plus r e to the rx minus 7 e to the rx is equal to 0. Do your isolation. You're looking at r squared plus r minus 7 equals 0. We'll zero this out. You can see this right here is not easily factorable. Therefore, you have to bring in your quadratic formula. You have a, b, and c. You're looking here at minus 1 plus and minus b squared, which is a 1 minus 4 times 1 times minus 7 divided by 2 times 1. You know, minus b plus minus square root b squared minus 4ac divided by 2a. A, b, and c, the coefficients. When you simplify all of this, you're looking at minus 1 plus and minus, but again, we still have two real roots. These are legitimate roots. They just are not whole numbers. You'll have here 1 plus 28, which will be a square root of 29 over 2. In essence, you're looking at a minus 1 plus root 29 over 2, and then you're looking at minus 1 minus root 29 over 2. Those are your two real roots. How will you put them in your answer form? You can. And now I'm bringing the constant right here. Y is equal to a e to the power of minus 1 plus root 29 over 2. X being applied to this entire expression here. This right here is an expression plus b e to the minus 1 minus root 29 over 2. All of this to apply to x. But you see, here's our solution to your question. Y is equal to a e to the power of minus 1 plus root 29 over 2x plus b e to the power of minus 1 minus root 29 divided by 2x. The generalized solution form for this differential equation right over here. And that question has been completed and the answer is good. This will bring me to the end of this video, and now you are seeing linear homogeneous second order differential equations are not hard. Keep in mind they're of this form. Your unadulterated, your uncorrupted y factors or the derivatives with respect to y's attached easily to basic functions or constants and always equaling a 0. You're not looking here at any modification of your y variables or your derivative of y's, hence they're the linear form and they're easy to handle. Thank you for watching.